Hello friends, let's study new lecture on linear algebra. In today's lecture, we will be talking about matrix norms, orthogonal matrices, then matrix factorization, and many other topics. So in this lecture, we will study a chain of concepts, and each one is a prerequisite to another one. We already had norms in case of vectors, and for vectors, we learned that the norm is size, or you can say length of a vector. Length or size of a vector is called as norm. We have the same keyword in the realm of matrices, which is, you can say, the magnitude of matrix as norm. We have different kind of norms. The first one is Frobenius norm. In here, the square root of the sum square of the element is the norm. Very simple. We will first square of each element, then we sum up them together. It's very easy, right? So the square root of the sum of the squares of all elements, this is like Euclidean norm of a vector. So what we do here, we have on matrix X, for example, with 4 elements, just a square root of so minus 1 square plus 2 square plus 0 square plus 5 square, which gives us the square root of 13. The next norm is Manhattan norm, also L1. This is very simple sum of elements, and we will find the max of them. So what we do here, first, this is J. It means we go from column wise. We go for column wise. What we do here, we get the sum of absolute value of each column, then we get the max of them. With an example, we better understand. This is matrix A. What we do here, for the first column, absolute value of the first one plus absolute value of the second one, it gives us 3. For the second column, 7 plus 3 will give us 10. Then max of 3 and 10 will give us 10. Also, we have the same norm in case of infinity. In this case, we go for row-wise. Right? So what we do here, first we go for the first row, give us 8. The second row give us 5. Then max of 8 and 5 gives us 8 as the norm. We also have L21 norm in here. This is the sum of Euclidean norm of the column of a matrix. So what we do here, first we go for rows and then columns, right? First we get the rows, then the column. We first apply L2 norm along the column to obtain a vector with some dimension. Then we apply L1 norm to that vector to obtain a real number. The next norm is considered as a spectral norm. The spectral norm is the largest singular value of a matrix, as you can see here. So it is also known as 2 norm. So we can think of it as the maximum scale by which the matrix can stretch a vector. In here, we will go for the maximum singular value. Maximum singular value. The maximum singular value is the square root of the maximum eigenvalue. So what we do here, we have a matrix like A. So we have 2 steps to follow. First of all, we go for ATA transpose A multiply itself, which will give us this one. Then we will go for finding the eigenvalues of this B matrix that we have generated as the product of the transpose of the matrix by the matrix itself. You already know how to find. Finally, we will come up with lambda 1, lambda 2, and lambda 3. Then we will find out the square root of the largest. The square root of the largest, this one will give us 10.967 as the spectral norm of this matrix. Also, we have max norm, which is the simply maximum value of an element of the matrix. Then norm preserving. A linear transformation can preserve the Euclidean norm, and this is somehow called as isometry or orthogonal transformation. Such transformation maintain the distance and angle of the vector. So by maintaining the distance and angle, and this ensure that the norm of the vector, or you can say magnitude, is not changed. So we can say the is unchanged. This is called as norm preserving. We already know that if inner product of 2 vectors is 0, then we can say that these 2 vectors are orthogonal. So remember that the dot product can be in 2 ways. If we go for algebra point of view, we can say that, for example, u dot v is equal to what? These are 2 vectors, is equal to u1 multiply v1 plus something plus un multiply vn. This is algebra. In case of geometric, we can say u dot v is equal to u dot v cosine theta, where theta is the angle between them. Also, we know from the previous lecture that a vector u is called as a unit vector if the length is equal to 1. So, based on all this information that we have, we can define orthonormal vectors. Orthonormal vectors. Vectors are considered as orthonormal to each other if they are, first condition, they are orthogonal. Second condition, their length is equal to 1. So if two vectors, they are orthogonal to each other and their length is equal to 1, then we call them as orthonormal vectors. Then for any non-zero vector like v, this one, v divided by norm, is called as normalized vector. This is called as, so v divided by norm is called as normalized vector. So here is one example. We have vector u and vector v. So u dot v is equal to 0. It means these two are orthogonal. Then we go for the norm. Norm of u is equal to square root of 21. Norm of v is equal to square root of 14. Then we go for the equation. This should be 1. This should be 1. So u divided by norm of u is this one, and v divided by norm of v is this one. If you get the length of these two, it's equal to 1. So first condition is okay. Second condition is okay. Then we say these two are orthonormal. These two are orthonormal vectors. Not only vectors can be orthogonal to each other, but subspaces also can be orthogonal to each other. If every vector in subspace A is orthogonal to every vector in subspace B, then we say these two subspaces are orthogonal to each other. It means A dot B is equal to 0. What is the meaning of subspace? For example, this is one subspace A, this is one subspace B. Subspace means any vector in this subspace should have second and third component as 0, and the first one can be anything. For example, 1, 0, 0, right? In here, the subspace is something like this, 0, 1, 1, right? This is subspace B. And if you do the dot product, in a product, then you will come up with 0. It means it doesn't matter what is the A1, B2, or B3. Any vector in this subspace is orthogonal to each other. That's why we can conclude that these two subspaces A and B are orthogonal to each other. Functions also can follow the characteristics of orthogonality. Orthogonal functions are a set of functions that exhibit orthogonality properties over a specific interval. This is the point. We cannot say that two functions are orthogonal in any range. No, in some specific range, we can define them as orthogonal, right? Functions are considered as orthogonal if their inner product is equal to 0. Their inner product is equal to 0. So, for example, here we have two functions, fx is equal to x, gx is equal to 1. So, we want to try based on some interval of -1 and 1, for example. So, f and g, inner product of this one, is equal to integral of a to b, where the a is -1 and b is equal to 1, x multiply 1 dx. And based on the integral regulation, integral of x is equal to x2 divided by 2 from a to b, where a is equal to -1, b is equal to 1, then finally you come up with 0. That's why these two functions are orthogonal to each other. But remember, functions are orthogonal only on some range, not always. So the next one is orthogonal matrices. Square matrices can be orthogonal if their columns make orthogonal set of vectors. So we can say like n to n q matrix is orthogonal if the columns are orthonormal to each other. Orthonormal columns means their columns are orthogonal to each other and their length is equal to 1. Then we can say a linear operator like T can be orthogonal operator if its standard matrix is orthogonal matrix. If we want to check whether a matrix is orthogonal or not, we need to show that the columns of the matrix are distinct and they form an orthonormal set. Then we can conclude that is orthogonal or not. So these are the properties of an orthogonal matrix. If Q is an orthogonal matrix, then Q multiplied transpose is equal to IN, identity matrix. Q is always invertible. Q inverse is equal to transpose of Q. The multiplication of Q into two vectors is the same as the multiplication of two vectors itself, and QU is equal to U. That's why we call it as orthogonal operator. So here is one example. We want to check whether this matrix is orthogonal matrix or not. This is a 2 by 2 matrix, a square matrix. So what we do here, so we have two columns here. First, we check their orthonormality. If these two vectors are orthonormal to each other, then we can say the matrix is orthogonal. So 2, first we go for the multiplication and it's 0. It's okay. Then we check the length of this one and we come with 1. The second condition is okay. Because the columns are orthonormal to each other, then we can say the matrix is orthogonal as well. We have another way if, for example, this AT dot A is equal to AN, based on this condition that we have, then we can say this is okay. AT, right? So we have a matrix here, and we want to check the A multiplication of A by its transpose, if it's equal to identity matrix or not. If it's okay, this satisfied, then we say this is an orthogonal matrix. This is our matrix, so we try this one by transpose, and you can see this is not an identity matrix. That's why we can say this is not an orthogonal matrix. We already studied many techniques for solving system of linear equations. However, many of those approaches suffer from some error like round-off error, which apply to larger matrices. Now, we want to study how to factor a matrix as a product of matrices with desirable properties. Then we can use easy method to solve the system of linear equation. In general, if you have a matrix like m by n and the columns are linearly independent, then we can factorize or decompose. We can call it a QR decomposition. In here, we try to split our matrix to two matrices. One is called as Q matrix, another one is called as R matrix. So the first matrix is an orthonormal, it means the columns are orthonormal, and the second matrix R is an upper triangular matrix. So we express matrix A as the product of an orthogonal matrix like Q and upper triangular matrix like R. This QR decomposition can be used for solving linear system, least square problems, and eigenvalue problems. So we will have two factors, Q and R. Q is Mn with orthonormal columns, and R is upper triangular matrix. Let's try this example. So we have one matrix here as matrix A. We want to split this matrix to two matrices. We will come up with these two matrices, 1 and 2, Q and R, right? So let's try. To come to here, we have to find three columns, Q1, Q2, and Q3, and also here the elements R11, R22, R13, R22, R23, and R33. So I will show you how to find these components in order to form these Q and R matrices. So we start from here, the matrix A. So we will have this Q prime as a temporary or helping variable. So first of all, we say Q prime is equal to A1. This is A1, this is A2, this is A3, right? A1, A2, and A3. So Q prime 1 is equal to A1. So this is the first step. In the second step, we go for R11, right? R11 is the length of this A1, which is the square root of 2. Then we will form the Q1, the first column in Q matrix, as 1 divided by the norm of Q1 prime multiply Q prime 1, right? Which is this one by root square of 2 multiply this one, which give us this. Then we move to R1 and 2. R1 and 2 is transpose of Q1 multiply A2, which give us this one. Then we form Q prime 2 as A2 minus R1 and 2 multiply Q, which give us this one, right? Then we go for R2 and 2, which is the norm of Q prime 2, and we will come up with this one. Then, based on this one, we will form the Q2 as the Q prime 2 divided by the norm of Q2, which give us this one. Then, we go for R1 and 3, which is Q1 transpose multiply A3, and based on this simple multiplication, you will come up with this one. Then, we go for R2 and 3 as the transpose of Q2 multiply A3. This is Q2 transpose, this is A3, and which give us this one. Then, we go for Q prime 3 as the A3 minus R13, Q1 minus R23, Q2. This is come up with this one. And R33, this is called as Q prime 3. And the norm is this one. Then we will get this one, Q prime 3 divided by the norm of Q prime 3, give us this one. Then we will collect all together, Q1, Q2, Q3. R11, R12, R13, R22, R23, and R34. If you want to check whether you did good or bad, just multiply Q by R. So this is Q multiply R, which give us our original matrix. It means it's okay. This is called as, the QR matrix. The procedure that we follow is called as Schmidt process. This is a kind of process that we use for QR matrix factorization. This decomposition factorize a matrix A into Q and R. And in here, we follow this Schmidt process in order to form the Q and R. Let's see some other properties of orthogonal matrices. Orthogonal matrices have some properties like determinant of a orthogonal matrix is equal to plus or minus 1. In the case of two orthogonal matrices, the product of two orthogonal matrices is another orthogonal matrix. The inverse of an orthogonal matrix is an orthogonal matrix. And if a matrix is orthogonal, then its transpose is also orthogonal. These are the properties. Now we want to try applying the properties of orthogonal matrices on orthogonal operators, because a linear operator is orthogonal if and only if its standard matrix is orthogonal. We can come up with this statement. Suppose T is a linear operator, T is a orthogonal operator, then we can state some equivalent statements like T is an orthogonal operator. It's equivalent to Tu dot Tv is equal to U dot V. It means unchained preserving, right? And the norm of Tu is equal to the norm of U. T and U are orthogonal operator, then Tu and T inverse are orthogonal operator as well. So let's see some example. We want to find orthogonal operator T on our cube such that T of this vector is equal to 0, 1, 0. Suppose V is equal to 1 by root square of 2, 0, and 1 by root square of 2. Suppose that T is such an operator, with a standard matrix of, like, for example, A, then we can say that AV is equal to E2 and V is equal to inverse of A by E2. Remember that a standard matrix has columns that are the image of the vector of the standard basis. For example, you can say T of 1, 0, 0, or T of 0, 1, 0, and T of 0, 0, and 1. These are called as standard matrix. Then A is an orthogonal matrix, is A transpose multiply A is equal to identity matrix. Then we can say that T satisfies that T is equal to E2 and T is equal to. Then it is enough to choose A so that A transpose is orthogonal matrix whose second column is V, as you can see here. The second column is V, and here doesn't matter. For example, this one we can go for this one, and this one we can go for this one. Then we can go for A inverse, and you can see that A is equal to the transpose of A inverse. The next concept is symmetric matrices. A symmetric matrix, as you know, it's a kind of square matrix that is equal to its transpose. This is called as symmetric matrices. If you flip the rows and column, then it will remain the same. Symmetric matrices have several properties like real eigenvalues and orthogonal eigenvectors. The eigenvalues for symmetric matrices are real, based on this. And if U and V are eigenvalues for a symmetric matrix that correspond to a distinct eigenvalue, then U and V are orthogonal. These are the characteristics of symmetric matrix. Here is an example. We want to, this is a symmetric matrix. So transpose is equal to same. We want to find an orthogonal matrix like P such that P transpose AP is a diagonal matrix. So we need to find orthonormal basis of R2 consisting of eigenvectors of A. So first of all, we go and try to find out the eigenvalues. You already know how to find the eigenvalues based on the determinant of A minus lambda in. Then we go and find out the eigenvectors by substituting and coming back. Then we will come up with these two eigenvectors. So these are eigenvalues and eigenvectors. Also, as we already studied the orthogonality of two vectors, these two eigenvectors are orthogonal because their dot product is equal to 0. So they are orthogonal to each other as well. This is called as orthonormal basis of R2. You remember how to find it. This one, this is simply of 1 by the norm of U multiply U. We already know this one. We already did it in several slides ago. Then for P, we can go for this one here, which is equal to this one, and D is 6006. If you try this one, this is a kind of diagonal matrix. So we can say N to N matrix is symmetric if and only if there is an orthonormal basis for Rn that consisting of eigenvectors. Then in this case, there exists an orthogonal matrix P and diagonal matrix D in such a way that P transpose AP is equal to D. For a symmetric matrix like A, it holds true that if U and V are eigenvectors corresponding to distinct eigenvalues, then U and V are orthogonal to each other. This means their product of UV is equal to 0. This property is a consequence of the spectral theorem for real symmetric matrices. Based on this property, we ensure that the eigenvector corresponding to different eigenvalues are perpendicular or orthogonal to each other. So this is the way that we can try. Look at the example again. This was our matrix, and we come up with these eigenvalues and eigenvectors as a S-span. Then we come up with P and D. These properties is holds A equals to PDP inverse. You already know this one for diagonalization. And two new property we have. Transpose of P multiply A multiply P is D. This is a new characteristic. And A is equal to PDP transpose. So we already have PDP inverse for diagonalization. The same we have here. P is equal to PDP transpose. These are the new characteristics that we studied. For any symmetric matrix, it can be decomposed into some of very simple matrices. This is called as spectral decomposition. Then once we have decomposed our matrix, we can prove the deep results about matrices. For example, we have a matrix as a n by n matrix. and we have some orthonormal bases like u1 to un, and these are the eigenvectors of A with these eigenvalues. Then there exists symmetric matrices P1, P2, and Pn that these characteristics are there. So A is equal to multiplication of eigenvalue to these symmetric matrices. Rank of Pi is 1 for all I. This matrix, symmetric matrix multiplication is the same, and J is the same, and the rest that we can see. So let's see the last example for understanding spectral decomposition. Suppose we have a matrix like 1, 5, minus 2, 5, 4, 5, minus 2, 5, 1. Then you know that A is equal to PDP inverse. So our D is this one, and P is this one. You already know how to find it. Then we can say A equal to 9 of the first column, and the transpose of it plus minus 6, this one and its transpose, plus 3 of this one and its transpose. Then you come up with a linear transformation. As you can see here, 9 by, if you do this multiplication, you will come up with this, minus 6 plus 3. So these are what? These are eigenvalues, this eigenvalue, 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 and these are P1, P2, P3, P1, P1, P2, and P3. These are some symmetric matrices that they follow these kind of properties. This is called as spectral decomposition. So we have one matrix A here based on the P and DP matrices that we already know. These are the eigenvalues. These are eigenvectors. Based on eigenvalues and eigenvectors, we can decompose our matrix. It means what? First eigenvalue, eigenvector, it's transpose. Second eigenvalue, second eigenvector, it's transpose. Third eigenvalue, third eigenvector, it's transpose. Then if you bring it all together, then this is the spectral decomposition of these matrices. Lower upper decomposition or lower upper factorization, or in short, LU decomposition, is also a helpful technique to decompose a complex matrix into some easier matrices. So what we want to do, we want to convert or split our matrix as the product of a unit lower and upper triangular matrices. What we want to do, for example, we have a matrix like A, and then we want to convert it to L and U. This L, the main diagonal is 1. Here can be anything, and the upper side is 0. In the case of U, these 3 are 0. The rest can be anything. This star, it means can be anything. This LU decomposition will help us in many areas, like we can use this decomposition for solving linear systems to solve, very complex linear equations efficiently, because it will help us to simplify the process of finding the solution by decomposing the matrix into lower and upper triangular matrices and making it computationally advantageous. Then we can use for inverse matrix computation, because it facilitates the computation of inverse matrices, which is valuable in various mathematical and computational contexts. It can be used for determinant calculation. It can be used for optimizing database queries, like in database management system. LU decomposition, particularly square root decomposition, helps optimize queries by dividing data into blocks or chunks. It can be used for numerical linear algebra and many others. So, okay, this is an example. We want to try to decompose this matrix into 2. Here we go. This is our matrix. This is our original matrix. And we want to come to this L, right? So L is, how is L? We need to find 3 components for L. 1 for here, 1 for here, and 1 for here. We have to convert these 3 to some numbers, right? And this matrix should be changed into something like this, right? It means, the low 3 should be 0. It means this should be converted to 0. So what we do here, we can use row operations, elementary row operations. But the problem is, this is the only form of row operation we can use. One row is equal to the row minus k times of another row. So this is the only allowed row operation we can use, right? So if this is our matrix, first of all, we change R2, because we want to change this one, right? We want to change R2 minus 5 by 2 times of R1, right? So this is our k. So the first k, you can say k1 is equal to 5 divided by 2. Okay, this is the k1. So if you do, then we will have this one as 0, 4, 5 by 2, and this is the same, right? And in here, we will save this k1 in here, row number 2, column number 1. So k will be saved into here. This is the first step. Then we move to another step. This is what we found in the previous step. In this time, k2, you can say k2 is equal to 2. And row number 3 is row number 3 minus 2 times of row number 1, right? Row number 3, because we want to change this one to 0. Row number 3 minus 2 times of row 1. So this one will be 0, minus 3, and minus 4. And this K2 will be saved into here, in the L matrix, right? Into L matrix. Then in the next round, so we have 1, 0 here, 1, 0 here, we have to change this one to 0. In this case, we will go and do R3, this R3, plus 3 by 4 times of R2. It means K3 is equal to minus 3 by 4. And if you do the calculation, then you will finally come to what, 0 and 0. This one remain the same. And this one will be saved in here. As you can see, L is in our desired format, right? L is in our desired format, and U is also in our desired format. So this is our U matrix, this is our L matrix, right? So very easily we converted one matrix to U and L. So what we do here, this is L and this is U, right? If you want to check whether this calculation was correct or not, just we do L multiply U, it must be equal to A, right? So this is L matrix, this is U matrix, and if you do the calculation on simple matrix multiplication, you will come up with A. So this is called as LU decomposition or LU factorization. I hope you understand, and please feel free to ask me if you have any questions about this matrix factorization and the composition that we studied in this lecture. Thank you.